A second order step response can have a steady state value, a peak time, rise time, percent overshoot, and settle time. Given some graph, some vertical quantity, call it y, of any unit versus time, a step response could look like this. Where the steady state value is the final value after the transient. The value of y right there is the steady state value. And this is called the peak value. And this is called the peak time. That's called an overshoot. The steady state value has been overshot. And so there's a percent overshoot associated with that first peak. There's also a settle time. Settle time relative to the plus and minus 2% values. If this is 2% higher than the steady state value, and this is 2% lower than the steady state value, then the settle time is the time at which the signal enters that region, never to leave again. And that time happens right here. That's the settle time. There's also a rise time. The rise time is the time it takes to go from 10% to 90%. If this is the 10% value, and this is the 90% value, then the rise time is the time between those two. So the rise time is the time from here to here. That's the rise time. We have settle time, peak time, rise time, and percent overshoot. Those time domain parameters are related to system transfer functions in the S domain. For example, here's a standard second order transfer function where A and B are numbers. If A is divided into three parts, 2 zeta omega n, and B is equal to omega n squared, then zeta and omega n turn out to be directly related to some of those time domain parameters. For example, percent overshoot is equal to 100 e to the minus zeta pi divided by the square root of 1 minus zeta squared. And the peak time is equal to pi divided by omega n times the square root of 1 minus zeta squared. We see those time domain parameters directly related to these particular S domain parameters. Also, settle time is equal to 4 divided by zeta omega n. And the poles of the transfer function have interesting relationships to zeta and omega n. The poles of the transfer function come from setting the denominator equal to 0 and then solving for s. If we complete the square, first subtract omega n squared from both sides, then add half of 2 zeta omega n squared, to both sides, then the left-hand side becomes a perfect square. And then when we take the square root of both sides and then subtract zeta omega n from both sides, we see a real part, negative zeta omega n, and plus or minus an imaginary part, j omega n multiplied by the square root of 1 minus zeta squared. These are the poles of the transfer function directly related to zeta and omega n. And a graph of these will show even more clarity. Here we see the complex plane, real axis horizontally and imaginary axis vertically. We see the two poles as the two dots, two complex conjugate poles plotted in the complex plane. The real part is minus zeta omega n, and the imaginary parts are plus and minus j omega n, square root of 1 minus zeta squared. The distance from the origin to either pole is omega n. And the angle that that radial line makes with the real axis is theta. Cosine of theta is equal to zeta. There's the relationship between those poles in the complex plane and zeta and omega n. All of this will turn out to be very useful later.